The James Webb Space Telescope has gifted us breathtaking images of the cosmos. These images are not just beautiful, they are, windows into the distant past. We see galaxies as they were billions of years ago, back when the universe was, young. Their light has traveled for eons to reach us. The JWST allows us to witness the universe's infancy. These images inspire awe and wonder. They also raise some pretty profound questions. The JWST is showing us something unexpected. The universe's expansion might be different from what we thought. This difference, known as the Hubble Tension, is a major mystery in cosmology. The universe is expanding, space itself is stretching, carrying galaxies away from each other. But how fast is it expanding? This is where the Hubble tension comes in. Scientists use two main methods to measure the universe's expansion rate. These methods give us different answers. This difference is the Hubble tension. It suggests that our understanding of the universe might be incomplete. To understand how fast our universe is expanding, astronomers have developed two main methods, each relying on very different cosmic clues. The first method looks back to the very dawn of time, using the faint afterglow left behind by the Big Bang itself. This afterglow is known as the cosmic microwave background radiation, or CMB for short. It's a kind of fossil light, a snapshot of the universe when it was just 380,000 years old, a baby in cosmic terms. The CMB fills the entire sky, invisible to our eyes but detectable by sensitive instruments, and it holds a wealth of information about the universe's earliest moments. This ancient radiation has been journeying across the cosmos for nearly 13.8 billion years, carrying with it subtle imprints of the universe's structure and composition from its earliest days. As these photons traveled, they passed through clouds of gas, clusters of galaxies, and the expanding fabric of space itself, all of which left their mark on the CMB's delicate patterns. By carefully studying these patterns, tiny temperature fluctuations and slight differences in polarization, scientists using the Planck satellite have been able to reconstruct a detailed picture of the early universe. The Planck mission, launched by the European Space Agency, mapped the CMB with unprecedented precision, revealing the seeds of galaxies and the overall shape of the cosmos. From this data, cosmologists can infer the universe's age, its composition, and crucially, how fast it should be expanding today, a value known as the Hubble constant. This method, rooted in the physics of the early universe, gives us a prediction for the current rate of expansion. It's like looking at a baby photo and using it to estimate how tall that person should be as an adult, based on what we know about growth and development. The CMB method is powerful because it relies on well-understood physics and observations of the universe as a whole. The second method, however, takes a more direct approach. Instead of looking at the universe's childhood, it measures the expansion rate in the present day, using special stars called Cepheid variables as cosmic mileposts. These remarkable stars brighten and dim in a regular cycle, and the period of their pulsation is directly related to their true luminosity or intrinsic brightness. By observing how quickly a Cepheid star pulses, astronomers can determine exactly how bright it really is. Then, by comparing this true brightness to how bright the star appears from Earth, they can calculate its distance with impressive accuracy. Cepheids are like cosmic lighthouses, their rhythmic flashes helping us map the vast distances between galaxies. Using powerful telescopes like the Hubble Space Telescope and now the even more advanced James Webb Space Telescope, astronomers have identified Cepheid variables in nearby galaxies. By measuring their distances and then observing how quickly those galaxies are moving away from us, scientists can directly calculate the current rate of cosmic expansion. This approach, known as the distance ladder, builds up our understanding step by step, from stars in our own galaxy to galaxies millions of light years away. By comparing the results from these two methods, the ancient light of the CMB and the present-day measurements using Cepheid stars, astronomers have discovered something surprising. The two methods give slightly different answers for how fast the universe is expanding. This puzzling discrepancy is at the heart of one of modern cosmology's greatest mysteries. The problem is, these two methods don't agree. The Planck satellite tells us the universe is expanding at about 67 kilometers per second per megaparsec. But observations of Cepheids with the Hubble and JWST give us a faster rate, around 73 kilometers per second per megaparsec. This discrepancy is, honestly, significant. It's like measuring the length of a table with two different rulers and getting two different answers. Initially, scientists thought this difference might be due to errors in our measurements or our understanding of the stars we use as cosmic yardsticks. However, the JWST's incredible precision has ruled out those possibilities. The Hubble tension is real. The James Webb Space Telescope has added another layer to the mystery. Its deep-field images have revealed something astonishing: massive galaxies existing much earlier in the universe than we thought possible. These galaxies are unexpectedly large and mature for their young age, challenging our understanding of how galaxies form and evolve. This discovery is puzzling because it suggests that the early universe might have been a much more active and dynamic place than our current models predict. It's as if we expected to find toddlers, but instead, we encountered fully grown adults. Something is accelerating the growth of these galaxies, and honestly, we don't know what it is. The Hubble tension and the discovery of these unexpectedly massive galaxies in the early universe have sent shockwaves through the world of cosmology. These findings challenge the very foundations of our understanding of how the cosmos evolved after the Big Bang. The Hubble tension refers to a puzzling mismatch between two different ways of measuring the universe's rate of expansion, one based on observations of the nearby universe and the other on the cosmic microwave background, the afterglow of the Big Bang. Meanwhile, the James Webb Space Telescope has revealed galaxies that are far more massive and mature than our models predicted could exist so soon after the universe began. These cosmic surprises force us to confront the limitations of our current understanding. The universe, it seems, is not behaving according to the rules we thought we knew. For decades, scientists have relied on the so-called standard model of cosmology, a framework that has explained much of what we see in the cosmos. But now, cracks are appearing in that model, and researchers are being pushed to think outside the box. In response, scientists around the world are collaborating, debating, and exploring radical new ideas to explain these discrepancies. The search for answers is driving a new era of creativity and innovation in astrophysics. Researchers are re-examining old assumptions, developing new theories, and using cutting-edge technology to probe the deepest mysteries of the universe. One possibility is that dark energy, the mysterious force that makes up about 70% of the universe and is responsible for its accelerated expansion, is not a constant after all. For years, scientists have assumed that dark energy acts as a steady, unchanging force, stretching the fabric of space at a uniform rate. But what if that's not the case? What if dark energy itself evolves over time, growing stronger or weaker as the universe ages? If dark energy changes over time, it could help explain why the universe is expanding faster than expected in some measurements, and why we're seeing such massive galaxies so early in cosmic history. This idea would require us to rethink the very nature of the universe's most dominant ingredient, and could open the door to entirely new physics. In this scenario, dark energy might have started out weaker, allowing galaxies to form and grow quickly, before ramping up and accelerating the universe's expansion at a later stage. This would mean that the universe's history is far more dynamic and unpredictable than we ever imagined. Another possibility is that our understanding of gravity itself, as described by Einstein's theory of general relativity, needs to be revised. Einstein's equations have passed every test in our solar system and even in the wider galaxy, but perhaps they break down on the largest cosmic scales. Maybe gravity behaves differently when we look at the universe as a whole, compared to how it acts on planets and stars. If gravity operates in unexpected ways across vast cosmic distances, it could change how galaxies form, how they move, and how the universe expands. This would have profound implications for everything from the birth of stars to the ultimate fate of the cosmos. Some scientists are even developing new theories of gravity that go beyond Einstein, hoping to solve the mysteries that the Hubble tension has revealed. These new ideas suggest that the universe's expansion might be influenced by forces or effects we haven't yet discovered, and that our current models are missing key pieces of the puzzle. The search for these missing pieces is one of the most exciting frontiers in modern science. A third, even more mind-bending possibility is the existence of extra dimensions beyond the three spatial dimensions we experience in everyday life. While we're used to thinking of the universe as having length, width, and height, some theories suggest there could be hidden dimensions curled up at scales too small for us to see, or even vast dimensions that subtly shape the cosmos. These hidden dimensions could be influencing the universe's evolution in ways we're only beginning to imagine. They might affect how gravity works, how galaxies form, or even how time itself flows. If extra dimensions exist, they could help explain the strange observations that have left scientists puzzled and might point the way to a deeper, more complete theory of reality. Each of these radical theories, changing dark energy, new laws of gravity, and hidden dimensions, adds another layer of complexity to our cosmic picture. As we push the boundaries of knowledge, we're reminded that the universe is full of surprises, and that the quest to understand it is far from over. These are exciting times in cosmology. The universe is full of surprises, and the JWST is just beginning to unveil them. The Hubble Tension and the discovery of early massive galaxies are not problems to be solved, but rather opportunities to learn and grow. They remind us that the universe is a vast and mysterious place, and our understanding of it is constantly evolving. The universe is full of mysteries, and that's what makes exploring it so exhilarating. Every new discovery opens up new questions, pushing the boundaries of our knowledge and inspiring us to seek answers in the vast cosmic expanse. The Hubble Tension and the enigmatic early galaxies are not anomalies to be dismissed, but rather tantalizing clues guiding us towards a deeper understanding of the universe's grand design. As we continue to explore the cosmos, we must remember that our journey is not about finding all the answers. It's about embracing the unknown, questioning our assumptions, and refining our understanding with each new piece of the cosmic puzzle we uncover. The universe is a vast and ever-evolving tapestry, and we are privileged to be witness to its wonders. Don't forget to hit the like button, share, and subscribe for more fascinating discoveries.